This is Talk Universe. Welcome back to the show. This is our show for Wednesday, September 14th, 2016. I'm your host, Sir Charles Schultz, and tonight we're covering a fascinating subject. We've talked about virtual worlds. We've talked about all sorts of technologies and advances. Tonight we're going to talk about the possibility of making a new planet. Now, in our solar system, there are two planets that are terrestrial worlds that we could work with, Venus and Mars. And the question is, could we convert one or both of them into another Earth? This sounds like an outrageous prospect, but it's actually one that has a firm rooting in science. And yes, it would be a big project, a long-term project, but we know that the Earth was uninhabitable long ago, particularly when it first formed, and it took a lot for it to reach a point when organisms could survive on it. And as we know, a lot of that change happened because of organisms. The first organisms were not oxygen breathers at all. There was no free oxygen. And, a lot of scientists looking for life in the universe are looking for oxygen in the atmosphere of exoplanets as soon as they get the telescope capabilities to do that. And yes, if we found a planet with oxygen in the atmosphere, that would be a very strong indicator that there was life present. But how does a planet go from a barren ball of lava to a living world? And can we take aborted planets, failed planets that didn't quite make it, and convert them to a state where we can live on them and be comfortable? It can be done, and we're going to examine what would be necessary and the scale of those projects in this show tonight. So what would you call the process of converting a planet into a livable world? Let's say you started with a ball of rock that had a dirty atmosphere and temperatures of the days were wrong, and you decided to come in and do some engineering and fix it to make it like the Earth. Well, the name for that sort of process is terraforming. In a sense, we have some experience with it right now because we've been terraforming our own planet or anti-terraforming it. We've been changing things so that it is becoming unlivable. But we also have the technology to set things right. And this is a very important point to make. If you have the technology to create a new Earth to live on, you also have the technology to clean up the one that you're living on now. So we're going to examine terraforming for two reasons. And the first is, of course, because it's a great thought to be able to make a second home for humanity or a couple of extra homes for us to be on. But the other thought is that practicing this skill and doing the theoretical studies will teach us how to clean up a lot of the things that are happening on our own planet as well. So this is a very necessary thing for us to do. So we do have a couple of candidates in our solar system that might make a good second Earth, and that's Mars and Venus. Now, I'm going to start with Venus. It's closer to the Sun. It has about two-thirds of the distance from the Sun that the Earth does, and as a result, it gets about twice as much sunlight, a little more than twice as much. It's a very, very hot world. It didn't lose its primal atmosphere, and so it has over 90 times the atmospheric pressure we have on the Earth. Surface temperatures, because of all the high CO2 levels in the greenhouse heating, brings it up to about 460 degrees centigrade, a little hotter than that, around 900-something degrees Fahrenheit. And it actually rains sulfuric acid mist in some parts of the atmosphere as a result of the volcanic sulfate compounds that are present. So it's corrosion, it's pressure, and it's heating, and it is definitely not a place to be. So we would have to do something about that. But we'll get back to the atmosphere and the conditions in a little bit. It has about 92% of the Earth's surface gravity, so it'd be a little easier to get into space if you were able to establish yourself on the planet. We know that solar energy would be an excellent, excellent venture there because you have so much sunlight available. So there are some things to consider. On the downside, something struck Venus, apparently, in the distant past and basically stopped its rotation. So instead of having a 24-hour day like we have, its rotational period is 116 days and 18 hours. And because of how this combines with its spin around the Sun, its total day is actually 243 days long. So the two work against each other to make the day longer than its year. You're not going to get a normal day-night cycle out of the planet, and we're not going to be spinning it up. The amount of mass and energy would be incredible. But there are solutions to that. So we have a slightly lower gravity, which is fine. We have plenty of solar energy, which is fine. But we have this toxic, compressive, heated, crushing acid atmosphere that we have to get rid of. And we also have the issue of rotation. Basically, there isn't much. But we can get around those things. So Venus wouldn't be so bad if we could get around those issues, and we'll talk about that next. Mars, on the other hand, Mars is quite a bit farther from the Sun than the Earth, and it receives about half the sunlight that we do. It's a small planet. It's only about half the size of the Earth, a little more than that. And it appears to be an arid world, but we know that there's a lot of water present. Its atmosphere is extremely thin. Presently, the atmosphere on Mars is about 0.6% of the pressure we have. So it's almost a vacuum, and for many purposes it is a vacuum. But there's enough air present to actually have winds, effects, and weather, and we do see some clouds in the sky, and half of them are ice crystals and half of them are water vapor. So Mars is a possibility. Now, one of the things to consider is if we could put an Earth-like atmosphere on Mars, and I'm not saying that that'd be an easy task, but if we were to do it, the gravity is quite weak. It's only 38% of what we have on the Earth here, and so that atmosphere would be gone in about 50,000 years. It would blow off into space. But there are ways around that as well. If it at least reaches a point where we can walk around in shirt sleeve with maybe a respirator, it would still be not a bad place to be. So Mars has possibilities. Its year is almost twice as long as the year of the Earth, over 600 days in length. So its seasons would be longer. And it has a low enough gravity field that it would be very, very simple to leave Mars and get into space and to return from space to the surface of Mars. So from an industrial standpoint, it's a very good planet for settling. Now, one of the questions that we absolutely have to answer is this. It is quite possible that there are organisms on Mars today, and we don't want to wipe out another form of life just because we want a planet to live on. So we'd have to consider that. Right now, there are injunctions in place legally about contaminating the planet with terrestrial organisms and possibly destroying its biodiversity. And there are questions about whether there is life on Mars, bacteria in the soil at the very least. And we'll have to consider that. That's a moral and philosophical issue we do have to look at. But if that were not the case, it would not be difficult. In fact, it would be much easier to convert Mars into a livable world than Venus at this point in our technology. So it's a possibility. But Venus has a lot of pluses. And I think that we would probably select it instead of Mars as a place to terraform. So let's proceed with both sets of assumptions and go from there. Now, I'd also like to point out there's one other thing we haven't considered, and that is degrees of habitability. I mentioned that we could probably make Mars a place where we could run around in shirt sleeves as long as we had a respirator. So it's, marginally habitable in one sense. I think that we could reach a point very easily where plant life would take off all over the planet, and it would be everywhere. But for a human to survive, you would probably need a respirator or an air pack of some sort. Now, that's the sort of environment that would actually be quite achievable. And in a case like that, you could build structures or habitats that were airtight and did provide the level of oxygen that you needed. So it would be like living at altitude with an oxygen assist in many places on the planet. There are some areas where you could probably go around outside without a respirator. The bottom of the Hellas Basin could possibly be an achievable goal because it is the lowest area on the planet. It's clearly a deep impact basin and was probably the site of a huge ocean at one point that had probably the deepest seas on Mars. So there are some areas where that could be done. Venus, on the other hand, we would go for full habitability, the ability to live on it just as you do on the Earth. And I believe that's quite achievable, and we'll get into the technology of how that happens very shortly. So if we're looking at habitability, we can have places where you absolutely cannot live at all. The conditions should just be completely unreasonable. Or you can have places that are absolutely Earth-like, and then you have a whole scale of in-between. If we had a planet that had the right pressure and temperatures and moisture, but just didn't have enough oxygen, so you'd have to have a respirator mask, that's not such a bad trade-off for no place to go at all. And that could be something we could achieve actually pretty readily. Now, before I get into the meat of the show, I do want to do the Singularity Watch, and we've got some amazing and fascinating items. The university in UC Davis has produced a 1,000-core microprocessor, the kilocore processor, and it operates at 1.78 trillion instructions per second. This is an amazing thing to see. It has the equivalent of 621 million transistors in the chip, and it is basically 115 billion instructions per second at 0.7 watts. It's 100 times more efficient than any other traditional processor. The applications for it could be staggering. Imagine having 1,000 processor cores in your computer. Cell phones and top-end computers these days typically have from 4 to 8 CPU cores. This one has 1,000. I can only imagine what we'll be doing with it. The possible discovery, well, actually the discovery of a possibly habitable exoplanet in the Proxima Centauri system, which is only 4.2 light years away, is causing a lot of excitement. It's called Proxima b. It is about 1.3 times as massive as the Earth, which is not unreasonable, and it appears to be smack in the middle of the life-supporting zone, so that looks like a planet where we could very easily find life. It is in the proper area for liquid water to exist, and it looks like something that is going to cause a lot of consternation. We're starting to put together something called the Starshot, which is a probe that could get there in about 10 years and send us back some information on it. So that's causing a great deal of excitement. Possibly habitable planet right next door to our solar system. University of Waterloo chemists have come up with a long-lasting safe battery based on zinc instead of lithium ions. And it is for the storage of power and has half the cost of traditional batteries. This battery can't explode, is very safe, and it uses zinc and water, so it's not toxic, and its uses would be for storing off-grid generated power, for instance, such as from windmills and solar panels, so that you could have your electricity all night long, and even when the wind isn't blowing. So this could be a major advance, as many people are aware. The high cost of alternative energy isn't the systems to generate the power, or the power itself, but it's in the storage systems, and this could make a huge difference in how we generate and use our electricity. Now, one of the more exciting discoveries, USC Neuro Restoration Center and the Keck Medicine Center of USC have started to do some work on restoring movement to people who were paralyzed, and they've made some great success. They've been doing this for a while. They injected stem cells and other cells into the cervical spine of a 21-year-old paralyzed man. 2 weeks after the process, Chris Boson showed improvements. He was able actually to twitch his hands and feel some things. 3 months later, he's regained use of his arms and hands. Now, he was thought to have been permanently paralyzed. He was in a wreck where his car fishtailed, hit a tree, and slammed into a telephone pole, and they thought that he would be paralyzed from the neck down permanently. 3 months after the procedure, he can feed himself, write his name, and use a cell phone. And it looks like this is a wonderful way of curing severe trauma to the spine and paralysis. Work will continue, and hopefully this will reach the mainstream soon. We could get rid of paralysis in just a couple of years at this rate. The clinical trials going on now, they have had great success, and I think this is one of the things that shows just how far we're advancing. The singularity is near, and these advances are just a small sample of that. Now, my book recommendation is a book that's been written a while ago, and it's been updated recently. It's a book right in keeping with what we're talking about. It is The Case for Mars by Robert Zubrin. It was published in 1996. It was updated in 2011, and it's available on Amazon. And it makes a case for colonizing Mars and shows exactly how to create everything you need for a colony from materials that are present on the planet. And he goes through the case of how to generate your fuel, how to make materials such as glass and ceramic and building materials, and even covers the subject of terraforming Mars. The idea is to send a colony, set it up, and have them make themselves as independent as possible by using the local materials, which is the way any colony should be. The sensibility of it is what makes it such a great read. It is laid out in very clear layman's terms, showing how to generate fuel, how to generate building materials, how to find everything that you would need to set up a permanent colony. And it's based on a concept called the Mars Direct Mission, which he has eloquently explained, shows how to get people there without having to go through a lot of rigmarole. The Case for Mars is a very good book, and it points out how you can even create fuel from the atmosphere of Mars by capturing and compressing the carbon dioxide in the atmosphere, for example, and splitting it into carbon monoxide and oxygen. Well, this makes a great renewable low-yield rocket fuel. And it also shows that deuterium, a heavy hydrogen isotope, is available about 5 times more commonly on Mars than it is on Earth, and could be a very valuable export. So read The Case for Mars, and we'll be back shortly. So how do we go about taking a lifeless rock of a planet and turning it into a place we can call home? How do you make a planet inhabitable? When we look at the only world we know of with certainty in our solar system that has a good environment for life, we see a number of things that we would have to create on other worlds if we were to do the same thing there. And atmosphere, climate temperatures, water, those are the three major ingredients. After all, if you think about it, you could take a metal box, you could throw soil in it, a little sunlight, a little water, and some seeds, and you'd have plants, you'd have vegetables. Well, a planet is no different. It's like a huge incubator or terrarium. And most of the planets that we see, of course, are too cold or too hot, or don't have an atmosphere, or have too much atmosphere. And how do we go about creating the circumstances where that atmosphere and that temperature and that water presence would all be correct? Well, that's what we're going to get into here. Let's start with Mars. Suppose we wanted to make Mars something that we could live on. Now, we know it has only 38% as much gravity as the Earth does, so any atmosphere we create is eventually going to bleed off to space. But it's estimated that that would take about 50,000 years, and I think I mentioned that earlier. So if we did go ahead and create a livable environment there, we'd have quite a span of time in which we could do an awful lot of things. I mean, after all, how long is all of recorded human history? 6,000 years? I think we could achieve a lot in 50,000 years, particularly with the growth of technology we have. So how do we do it with Mars? Well, first of all, we know there's a lot of water inside the planet in the form of glaciers. The polar caps have water. It also has plenty of atmospheric gas, carbon dioxide. And you might not think that's a good atmosphere, but actually it's going to be very beneficial for us. And here's why. When we start heating up the poles of Mars, and we can do this in a number of ways, we begin to vaporize the CO2 snow and melt the water ice. And the carbon dioxide dry ice snow at the poles contains 2 or 3 times as much atmospheric gas as there is presently in the air of Mars. So simply by heating the poles and melting that dry ice snow, we can increase the atmospheric pressure substantially. And that would mean that the conditions for liquid water would also broaden. We would have more of a range for that liquid water to exist comfortably on the surface and persist for long periods of time. But there's another thing that happens here, and that is that the heat evolved in the process, or more correctly, the heat captured from the sun by greenhouse heating, will begin to melt a lot of that ice. Now, on Mars right now, the atmosphere is about 0.6% of air pressure that we would have here on the Earth. It is 6 millibars, or 6,000ths of one atmosphere. And if we were to raise that to, let's say, 2% of the atmospheric pressure we have here on Earth, we would see that the temperature would immediately jump. And the reason is simple. That very thin atmosphere that's present on Mars now is responsible for 20 to 25 degrees centigrade of excess heat from greenhouse heating. Now, a lot of people aren't aware that the greenhouse effect has a large effect on the Martian environment right now. And by tripling the air pressure or so, by melting those polar caps, we would be able to raise that substantially. The planet would become actually very hot very quickly. And that might seem crazy, but Mars actually gets a significant amount of heat from the sun, but it's simply lost to space right now. The planet has no way of effectively holding on to it. So how do you go about heating up a planet and melting its polar caps? Scientists are seriously proposing dropping nuclear bombs on the poles and using the heat to vaporize the CO2. Well, first of all, this is not a good idea. We're trying to create a planet we can live on and not spew radioactive materials into its environment in the process. Second, this is a very, very short-term, low-yield solution. In reality, what you really want to do is something a little more persistent, a little more permanent. I would suggest carbon black dust dropped all over the poles, and that could be done from a spacecraft. So you manufacture billions of tons of carbon black dust, and you dust the planet with it on the poles so that it absorbs more heat and raises the temperature simply from incoming sunlight. The other trick we can use, which is pretty simple, it would require some industry and some time, but this could be done. We have to have a factory that produces reflectors like big mirrors in orbit, and we direct more sunlight onto the planet, and we raise its temperature that way. Now, this is a very passive or benign method of doing it, and it's something that we can easily control. So how do we do this? Well, we would start by locating carbonaceous asteroids, a special type of asteroid that has a lot of moisture and organic materials trapped in their materials, and we would redirect them to Mars and put them in orbit. And the first thing we would do is set up some factories on these asteroids that would produce carbon black dust and organic materials needed on the planet, and start injecting them in the environment. And the second thing we would do is we would start making plastic, mylar plastic in particular, and covering it with aluminum or something to make it silvered. You've seen the silver candy bar wrappers and potato chip bags. This is the same stuff, but we make huge mirrors out of it in space, and we use it to collect and focus the sunlight on the planet. And we can put these things in orbit and even keep the night side of the planet warmed up all throughout the night, so that there would be continuous daylight around the planet for this period of time, and we would be heating it up with the express purpose of melting the snow and the glaciers that are under the soil. We know that there are huge, huge reservoirs of water ice in the soil of the planet, and by melting these, we would get the oceans to return. Now, this is an important step. Once we start injecting heat into the environment, and we start putting organic materials in the environment, and we're raising the temperatures and getting the water to come back, the water provides another function, and that is this. Clouds can keep heat from radiating to space. They can adjust the global temperatures very nicely, and water is a slightly greenhouse positive gas, but it also has the advantage in large bodies such as oceans or lakes of retaining heat. Water acts like a capacitor or a battery for storing heat, and our oceans do that for the Earth right now. You'll notice that many small island communities in an ocean stay warmer and more regular in their temperatures because the ocean water itself is banking all that heat absorbed during the day and then releasing it slowly at night. The same function can be performed on Mars very easily. So once we get the carbon dioxide into the atmosphere, we raise the air pressure, we melt the glaciers and the polar caps and the ice under the soil, we start bringing back water, which can trap the heat in bodies of water on the surface, and also we get cloud formation much greater than there is on Mars today. And believe me, there are significant clouds on Mars. We've got wonderful pictures of them. But we get the clouds to build up, and they keep the heat from leaching off into space at night. So here we have a major step in warming the planet, raising the atmospheric pressure, greenhouse heating, making the oceans, and retaining the heat in the oceans. Now, at this point, really what we need to do is get some organisms in there. And algae and lichens are really the best way to go. And what we do is we pick very rapidly growing plants. We might consider them weeds, but believe me, they have an important part in the environment. Weeds are very hardy, and they can produce atmosphere, they can produce all the oxygen you need, they can produce biomass for the soil, and they can spread uncontrolled over the planet very, very easily. And we start putting algae, grasses, dandelions, that sort of thing in the environment, and before you know it, the planet would turn green. Now, this is what we want. We want a self-sustaining environment. And once that happens, once those soil bacteria are planted, once the organisms are in place, we then go in and create whatever environment we need. And I would suggest we put fleets of robotic machines on the ground. We have robotic tractors on the Earth right now, and this can be done. And they could start sowing bacteria in the soil, and they could start planting things. And we could even use small drones to drop packages of seeds and the proper materials all over the planet. In a matter of a few months, we could seed thousands of square miles of the surface of the planet and see a real dent made in things growing all over the surface. So this would be a very viable step in terraforming the planet and making it something we can live on. So just to summarize pretty quickly, we would start by getting carbon black all over the surface of the poles and the northern and southern areas near the poles. We would put orbital mirrors together and start concentrating sunlight on the planet. And we would put organic matter all over in the environment, perhaps by crashing asteroids of carbonaceous material there. Other more ambitious stages would include scooping ice from the moons of Jupiter, perhaps, and shipping it back in a pipeline many years long, and delivering a continuous stream of water or methane or ammonia or other materials. And ammonia would be very beneficial. But in any event, we warm up the planet with mirrors and with carbon black. Don't have to use nuclear weapons. We also start getting the CO2 to increase in the atmosphere by that warming process, and we start the ice under the soil melting and the polar ice melting as well. This stabilizes the temperatures because the water in the oceans and new bodies of water will hold that heat overnight, so it regulates very well. The temperature of the planet goes up, the air pressure increases, water appears, water begins to appear everywhere. Then we go in with basically automated farm machinery. And we start dropping seeds, packages of seeds, fertilizers, all over the planet using drones and automated tractors. And in a period of 30 to 50 years, we would have an environment where you could walk around pretty much in shirt sleeves with an oxygen respirator, or maybe even better. So by using what we might consider to be weeds, mostly algae, lichen, dandelions, and some edible plants and some grasses, in just a few years, we could see life spreading all over the planet Mars, and could convert it into something that was at least marginally habitable. That would mean that humanity would have a second home. It wouldn't be a paradise, at least not in the beginning, but it certainly is doable. Even with the technologies that we have today, we know how this could be done. So Mars could become a second home for humanity, and one from which space travel can be done very easily because of its lower gravitational field. So this is a plan, really. If we could get enough resources together, get enough industry moving in space, and one of our previous shows we talked about was space mining, asteroid mining, and how it is a highway into space, just like the interstate highway system on the ground helped commerce and defense and industry. This is what we really have to do. We have to focus on this, because humanity only has one home right now, and it's extremely important, even in the eyes of Stephen Hawking, who's a very smart man, to get humanity to spread past the Earth and create other environments where we can live. Now, I know there are a lot of people who will object by saying, but wait a minute. There isn't even an ozone layer yet. How could plants or how could life of any sort live on Mars without an ozone layer? And the answer to that's actually pretty simple. Much of the life that you would initially seed would be in the oceans themselves, because the seawater itself provides a great measure of shielding. In fact, on the Earth, life didn't come out of the land for a very long time until the ozone layer appeared, and people have often asked the question, well, why didn't life spread onto the land earlier than it did, and why did it stay in the ocean so long? It's because there wasn't an ozone layer yet. So we would use the same trick. We would seed life into the oceans, we would seed life into the soil where it's under the soil and hidden away from that ultraviolet. And there are many plants, believe it or not, that produce natural sun blockers anyway. And so we would use specifically these types of organisms that have a resistance to it. And there are a number of other things we can do as well, but this is a very good, simple starting point. So consider, if life has the ability to resist ultraviolet light in many cases already, then we know that the ancestors of that life must have been exposed to ultraviolet at some point, and that's why they have the genes for that. And we can take advantage of what's available in nature, and we can also make some changes genetically to things ourselves to make it resistant to those conditions. So we have a lot of leverage in our hands right now. So at this point, we really only have a couple of questions involved with the project before we can do it. And one of them is, how long does it take? What sort of living conditions do you have when you're there? Because people are going to live in an uncomfortable condition if they think it's going to be a real yield, just like we did in the frontiers in the old West. And the other one is, how quickly can we pack? A lot of people would move today if they thought that this was possible. But finally, there's a very important one, and it is this. Who would own the resulting planet? I think we have to change our methods of ownership, government, and everything before we can successfully apply a project like this, because there could be a real fight otherwise. After all, we don't want some company claiming to own the planet, and we certainly don't want some of the governments on this planet claiming to own it. Think about it. This is Dolf Universe. Imagine a world very much like the Earth, closer to the Sun, but with a day cycle that you can tailor to make any length of day that you'd like. Imagine a world with valleys and oceans and seas and polar caps and forests, life in all directions. This isn't Venus, but it's a Venus that could be. Venus is very much like the Earth. Its size, mineral composition, its age, all those things are almost identical. But it's covered with the thickest, hottest, densest, most oppressive and corrosive atmosphere we know of. Venus's temperature is about 460 degrees C, hot enough to melt lead, and a lot of other metals would soften and fail. Even the landscape is slumped because of the high temperatures. The atmosphere is so thick, the pressure would crush you instantly, about 90 times as dense as our own. It's almost all carbon dioxide, runaway greenhouse effect, baking the planet. And it rains a mist of sulfuric acid, which would corrode and destroy a lot of machinery. So how do we make this into a second Earth? It's actually very simple. We would place an asteroid, a carbonaceous asteroid, or many of them, in orbit, the same scenario we would use with Mars. We'd start the factories making silver mylar reflectors, mirrors, and then we orbit them in strips. And as these mirrors begin orbiting the planet, we arrange them to blot out the sunlight, so that there is no sun falling on the planet Venus. And within a few short weeks, the heat radiates to the very cold sky, the darkness of space, and the planet's temperature begins to plummet. The carbon dioxide acts as a cooling fluid, just like water on a hot plate. It begins landing on the ground as it condenses out as the temperatures are falling. It carries the heat to the top of the atmosphere and radiates it to space. And in a while, the CO2, which is most of the atmosphere, begins to convert to a mist, to a liquid, and it rains out. And the planet is covered with an ocean of CO2. And in a bit, the temperature drops even further, and that ocean freezes to CO2 snow, dry ice snow. Then we have real leverage, because the atmospheric pressure is only about 1.5 times as high as it is on the Earth, and it's all nitrogen, almost all nitrogen. Which is fine, because plants and animals will need that to fix into their bodies and to make into biomass for the environment. So a sizable amount of it will be consumed by life once it's established. Now there is that other pressing issue, and that is the sulfuric acid. What do we do about it? That mist will condense and the sulfates will rain out on the ground. I should say the sulfuric acid will. We can handle that. It can be neutralized. Now, we end up with a planet that has blocks of dry ice, fields of dry ice on its surface. We would send in machinery and set up factories that did nothing but split the dry ice, because carbon dioxide is, after all, simply carbon and oxygen. So we set up factories that split the carbon dioxide and release the oxygen into the atmosphere and sequester the carbon where we need it, because it's going to be necessary for biomass. The nitrogen is fine. We can leave it as it is. Sulfuric acid, I suspect once we get the environment moving, it will get rid of itself. But if we had to, we could split it into sulfur, hydrogen, and oxygen. We literally could produce water and sulfur from splitting sulfuric acid. Water's good for the environment. We need the hydrogen. So there are things we can do chemically once we've reached a condition where the atmosphere condenses. And we do that by blotting out the sun. Now here's an interesting thought. Once those big mirrors are in space and we control their actions, their angle, their placement, we now allow them to continue to circle the planet, but we use them as louvers to reflect the sunlight onto the planet any way we wish. In other words, even though Venus doesn't spin on its axis the way we would like it to, the plan of spinning the planet to produce a day and night cycle is ridiculous. Instead, we use mirrors to change where the sun is shining on the planet, and we create the day and night cycle we like on command. This is the beginning of terraforming the entire planet, and it's a very simple and straightforward plan when you think about it. Mirrors blot out the sun and cool the planet. Later, the same mirrors act to create the day and night where we want it, under computer control. So here we have a brand new planet, sterile and waiting for the mark of life. Now, the Mirror project is probably a 20-year cycle, something that would take about that long. And the interesting part about it is, once we have the first factory in orbit to produce the first mirrors, we know exactly how to produce the rest. and we simply duplicate our efforts until we have millions of computer-controlled mirrors orbiting the planet. And this is also where we would place our solar power stations. So Venus has a second advantage, and that is it is very close to the Sun. And by integrating the mirrors and the solar power system, we end up with all the power the planet would ever need, and we don't have to burn any fuel, so we don't have to have any power stations on the ground. We simply beam that collected electrical power down to the receivers on the planet, and we have an entire utility system as well as a new environment to work with. Now, the biggest issue with Venus is oceans. We would need a lot of water. And it is quite possible that all the water we need would exist underground. So the reason for this is hydrogen in the form of methane and ammonia and hydrogen itself is trapped in the minerals that form the planet before the planet is actually made. And understand something, when a solar system forms, the star is generally not yet ignited. The planets are forming before the star ignites. And what this means is that the volatile materials, the materials that are blown away by solar wind and light pressure and evaporate very easily, are not yet lost. That doesn't happen until the sun ignites, and the light pressure and the solar wind push those chemicals away from the inner solar system out to where it's cold enough that they can condense. Well, the Earth, Mars, Mercury, all the inner planets condensed and formed before the sun ignited, and as a result, they contain within the bulk of their minerals all of the volatile materials that form atmospheres and oceans. So it's quite possible that just as we have found massive ocean quantities of water trapped in the rock inside the Earth, that those same materials would exist inside Venus. And if that is the case, then we may be able to drill wells and allow that water to escape and become a part of the environment. There may be enough water inside Venus to do the job. And if not, we know where there's plenty of water ice in our solar system where it could be retrieved. And that, of course, adds a lot of time to the project, but it's something that can be done. So we do end up with a second Earth, and it is an Earth that we have manufactured the day and the night cycle for. And it is a place that we could absolutely make a paradise. We would not have any need of fuels. We wouldn't need petroleum there for burning. If any form of hydrocarbon or petroleum existed within the planet, and that's also possible, then it would be used for the creation of the things we need. And I say plastic, I don't necessarily mean that we would be making plastic the way we do on Earth. It's certainly a useful material, but we've let it run just out of control. But we do need industrial compounds as lubricants and the feedstocks for making many of the products that we do need to stay alive. When you start thinking of petroleum in this way, you see it for what it really is and how valuable it really is. And here on Earth, we've done irreparable damage, perhaps irreparable. I think that we can actually fix it, but it's going to take an awful lot of effort. It might not be as much effort as is necessary to terraform a planet, but we're certainly headed that way, and unless we change what we're doing here on the Earth today, immediately, we're going to be in a situation where we would need another world very quickly. That's something we really don't want to see. We're already poisoning the planet very badly here, but that is another issue. I think what's really important at this point is for us to realize that with a little bit of ingenuity, we could convert almost any place in the universe into a place where we could live. And the same principles that we're talking about here for an entire planet can be done on a much smaller scale and in a very practical way. For instance, nothing prevents us from going to the moon right now, digging huge caverns underground and creating amazing living facilities with what we know. After all, there are whole cities underground here on the Earth, and they thrive. They do very well. The issues we would have to confront are those of replenishing your atmosphere and cleaning your water and recycling everything completely. And that does place some tight restrictions on how you live. But realizing that it can be done means that at some point it will. And if you start looking at planets of that sort, or smaller bodies, the moon and other places, then nothing prevents us from living all over the solar system. Yes, it would be a little restrictive, but look at the city of Montreal. They have an incredible underground there, and nothing prevents us from creating an environment like that, a very comfortable one, basically anywhere in our solar system or anywhere in the universe. One thing that it really would mean, if we had any sense about us at all, is it would be an end of poverty, because if you have the resources to create entire worlds, then you also have the resources so that everybody can have a great standard of living. Everybody can live comfortably and with dignity. This is one of the most important things we have to take away from this, that if we have the power to change worlds, we also have the power to change our lives. So let's think about this. What if we took an asteroid and we created, let's call it a generation ship, something that would have a supportable environment on the inside, an inside-out world, and we spin it a little bit to give it some gravity, so that we have an artificial gravity interior, and we have the hills and the mountains and everything inside out, so that literally you're on the inside of a rotating cylindrical world, and you have a light source, like a gigantic light tube running down the center, and inside is sculptured into mountains and valleys and streams and living spaces, and you send this ship with a handful of volunteers to the next star system. They would have their own entire world and working biosphere inside this generation ship made of an asteroid, perhaps, and it could reach Proxima b, the new planet they've discovered just 4.2 light years away. And this is possibly an Earth-like world. Now, we don't want to go altering an environment and changing the organisms that are already there if we discover life elsewhere. And this is one of the objections possibly to terraforming Mars. We have a moral imperative to preserve the things that we discover and not destroy them. And if we discover that there are still organisms alive on Mars today, then we wouldn't want to destroy them and create an environment that is suitable to earthly life and lose that library of information and those organisms. That would be a real shame. And the same would be said for Proxima b, for instance, if it turns out there is life there. We're capable of a lot of engineering, and we're capable of doing a lot of things, and we apply technology to solve a lot of problems, but we always seem to fall short in the moral categories, and we have to consider that capability doesn't mean you must do a thing. We have a lot of capability that we don't exercise because we realize that it wouldn't be the right thing to do, or maybe a little more cynical note that some company doesn't see a dollar to be made in it. But the fact is, we have to be responsible for our actions and their consequences. And terraforming is one of those big action and consequence scenarios, something we really have to keep our eyes open for. Now, I believe that within our solar system, there are probably 40 or 50 places where we could spread out and live quite successfully. And I see it happening in our future. If we don't destroy ourselves, we certainly could occupy the solar system and have a myriad of viewpoints and habitats. And it just opens your eyes a little to think. You could be living on the surface of Mars or Venus if they're terraformed, or you could be living inside an asteroid such as Ceres, or inside of the moon, or almost any place you can imagine. There are approximately 35 places in our solar system that would classify as worlds, and possibly more. We just don't know. There's so much more to learn about our solar system right here, much less the ones outside of our solar system, the exoplanets. Now, when looking for another home for humanity, we've discussed terraforming planets, and there are a lot of planets in our solar system, and only a couple of them are suitable for terraforming, and a lot of them aren't at all, and we'll talk about that as well. There are some moons that we could do some things with. They won't ever be terraformed like the Earth, but there are ways of making habitats there that would be quite livable and quite comfortable. Take a lot of engineering, but maybe there are other options. We'll talk about that after the break. This is Dolf Universe. So what makes a planet able to be terraformed? What makes a planet livable at all? Well, there are some simple parameters. There are simple things we need to know about it. First of all, it has to be the proper distance from the sun or some other star. Now, if it's too close, no matter what you do, it's going to be way too hot to live. And that means that in most cases it will either lose its atmosphere or go into runaway greenhouse, and it will become incredibly hot or smothering, or a vacuum that's too hot to live on, like Mercury. In other cases, if the planet is too far from its star, it'll be so cold that water will freeze and it'll basically plunge into an ice age and stay that way. But there are other things to consider also. Planets that are too small won't retain an atmosphere or won't retain it well enough. And Mars is pretty borderline. Its air is very close to being a vacuum. It actually has about the same density as the material inside a thermos bottle. It's a near vacuum. And other planets with a little too much gravity won't lose enough atmosphere, and they'll remain with a very thick envelope of gas that's very difficult to get rid of. It depends on what the gas is, of course. But there's also the problem that a very large planet, a massive planet, will have too much gravity. And nobody would be comfortable living there anyway unless they stayed in a waterbed all the time. So you have a fairly narrow range of parameters. The planet has to be at a certain distance from the star where the temperature range is good. It has to have a certain range of mass where it can retain an atmosphere, but not so much gravity that it retains too much atmosphere or it's uncomfortable to live on. After all, even if you had a planet that had the same or nearly the same atmospheric pressure as the Earth, but it had 20 or 30 or 40% more gravity, then it would be too difficult to get off of the planet, and it would be also an uncomfortable place to live, and people who did live there would probably be subject to a number of illnesses. So we would have problems because experiments with centrifuges, putting animals under high gravity conditions, were done many years ago, and they found that in some cases they were quite healthy and they did well. In other cases, they found that fluid would begin to leak out of their circulatory systems. They would kind of leak to death. So there are situations where we can withstand gravity that is higher than what we're used to, but typically not for a long period of time. We're just not evolved to live in that sort of a circumstance. Now, knowing that a planet might be a little too far from the sun, we can actually fix that using technology. If it's a little too cold, we can actually bring in orbital mirrors and increase the amount of sunlight falling on the planet. We can do things to increase the planet's ability to absorb sunlight, like put carbon black or dark organisms on the ground that'll absorb the heat. But in some cases, we won't have a planet. Let's say we go to another solar system, and we discover that the planets there just simply are not suitable for terraforming, and we're stuck there. Well, what do? Well, obviously it makes sense. If you're going to send somebody on the mission, and it's going to take years to get there, you're going to send everything they need with them. It makes the most sense to bring, essentially, a terraformer starting kit. And that would consist of a great deal of, equipment, gene-engineered microbes to get an environment going, and engines and material for building factories and moving asteroids around, and doing the things necessary to render a planet inhabitable. But again, you may find some place that you arrive has absolutely no place for you to go. And so what do you do in a situation like that? Well, the fact is, we're actually quite adept at living in interesting circumstances, and we always find an answer, and one of them would be to find particularly large asteroids and hollow them out, or burrow into them, and rotate them to generate the right level of gravity that you would like to have. So we can build habitats that are not quite worlds, but have immense internal volumes, and whole societies and biospheres would fit inside. Now, what's interesting is if, let's say, you arrived in a solar system and on the journey, intelligence arose, and you didn't know that. Now, this is pretty unlikely because if you have that degree of technology, you're probably going to be quite good at seeing what's there. But let's say you showed up in a solar system, ready to move in, ready to terraform, and you discovered that somebody else was already there. Well, what would you do?
Well, it might make the most sense to burrow into an asteroid and hide there, if you could keep your signatures quiet, if you didn't want to be discovered. And so it's quite possible that there are a number of asteroids that have been converted into what's known as generation ships and travel from solar system to solar system. That would take an immense amount of energy, that's true, but it could be done. And a ship like that would be a world in its own, in a sense. It would allow you to live in it for many hundreds of years if necessary. And whole generations of people would live and die inside that ship, traveling to their destination, quite possibly. You see, the issue is the speed of light. If we can't get a ship to move faster than the speed of light, then we're restricted to traveling no faster than that, and that means that travel times could be prohibitive. Now, moving something as large as a ship that contains enough to set up industries and factories and terraforming would mean you'd have an incredible amount of energy available to do the job. And getting into a solar system, you're going to make a lot of light. You're going to make a lot of signatures that people will detect. Now, if that's the case, you're going to find that there's a restriction on just how fast you can accelerate that ship. Now, ideally, you could make a ship travel very close to the speed of light, and your travel time internally wouldn't be that long. It might actually be on the order of a few weeks or a couple of months or even a year or two, and that would be something that we could live with. That means that you would not need the incredible amount of resources that you would for a generation ship. But just the same, you probably wouldn't have the fuel to get back home after a journey such as that. So there is a middle ground, and that is to take hundreds of years to get there, or maybe a few decades, instead of being able to make it internally a year or two or less. And what that would mean is that you could carry a very large ship and have a moderate amount of energy expended to get it there. And this is just a relative thing. In terms of our technology, we don't even have the beginnings of what it would take to do that. But we know that there are no showstoppers, really. It's just a matter of increasing our technology, understanding how to generate more energy and store it, coming up with better fuels or propulsion systems. And when you stop and think about it, if that's capable, if we're capable of doing that, it's quite possible that hollow asteroid generation ships might be in our own solar system right now. They might be in solar systems all throughout our galaxy. You see, there's an interesting thing that happens. Let's say you have the technology to build a machine that, without the use of pilots or any human minds to operate it, it has enough AI, or artificial intelligence, to set up a shop once it arrives somewhere and begin making copies of itself. Sort of like a virus, it would spread out. So you make one of these ships, it's called a von Neumann machine, and you ship it to one of the nearby solar systems. And when it arrives, and let's say it can only achieve 10% of the speed of light, so it would take, 42 years to get to our nearest neighbor, Proxima Centauri. So when it arrives, it takes a while to set up factories and build copies of itself. And then it launches them off to nearby stars, maybe a dozen of them or so, or maybe by the time it's got a factory made, it can make 1,000 copies. And so it launches these copies in all directions to other stars. And they arrive at those other solar systems, and eventually they would cover the entire galaxy by spreading from system to system. Now we understand that this can be done. And the interesting thought about this is, if somebody out there were already making such ships, in the period of perhaps 1 million or 2 million years, their factory ships, their von Neumann machines, would already occupy every solar system. So this is a very interesting thought. Now, if we were to build devices like this, von Neumann machines, and send them to other solar systems, what we would find is that after a period of time, they had spent building their factories and making their copies and sending them off to other solar systems, we would discover that pretty soon we would have a network that spanned the entire galaxy. And information would be coming back from countless solar systems. There are estimated between 200 and 400 billion stars in our galaxy alone. And the amount of information coming back would grow constantly. So even if we're limited to the speed of light, for whatever reason, we could still get information from all over our galaxy, and it would come in a flood. It would never stop. So we would expect that other civilizations would have already done this. It isn't technically impossible. We're very close to having machine intelligence and nano hardware and other advances that would allow us to make self-replicating machines, von Neumann machines. So we expect that we should have heard signatures of life, such as radio signals, and there have been some near misses, from all over the sky. We expect that life should be everywhere, and we would also expect that there would be von Neumann machines or von Neumann probes in every solar system. And not only that, there should be many of them from many, many different civilizations. Unless they were programmed to self-destruct or something like that, we may be able to find the remnants of alien machines in our asteroid belt right now. And they probably wouldn't be big devices. They might be quite subtle. Now, if we were to use nanotechnology to create von Neumann probes, we could probably make them as small as dust, and we could probably launch them very close to the speed of light by using linear accelerators similar to what's used to fire particles up to speeds near the speed of light. In this concept, your von Neumann probes would be a bag of dust, and you would fire the dust in all directions all over the sky, and it would reach the other solar systems very close to the speed of light. And eventually, they could send up other probes from their systems that they arrived in, just as we're talking about. And in probably 100, 200,000 years, the whole galaxy would have probes the size of dust. Now, how would you find something the size of dust hidden in the asteroid belt? Well, you probably wouldn't. So again, there could be machinery from other civilizations all over our solar system, as well as other solar systems everywhere in the galaxy. And it's the sensible way to explore. You can stay at home and have all the data sent back to you. But if we take this one step further, we can soon see that if you could send a probe about the size of a pinhead or the size of dust, and it was full of nanotechnology, all the technology it needed to make duplicates of itself, it also could very easily carry all the information needed to start terraforming a planet. And like a germ or a virus, it would infect every potential candidate throughout the galaxy. And in the course of 1,000,000 years or less, every planet that could be terraformed, that didn't already have life on it, could become the host to one or more of these dust-like probes that would then begin terraforming the planets. And in a very short period of time, around 1,000,000 or 2 years, we'd have every terraformable planet in the galaxy full of life. The entire universe could be terraformed step by step by these dust-sized nanomachines. Our galaxy could already be in a phase of terraforming, and we wouldn't be aware of it. But we don't really see any sign of it yet. And that's a very interesting question. We know, technically, that we're capable of many things, and in the future we should be capable of much more. And terraforming planets is only one step to making our race, well, essentially immortal, unkillable. Humanity needs to spread out so that we have safe places for us to be, and a disaster on one planet wouldn't wipe out the rest of humanity. So the question is, where are all our neighbors? Are we early on the scene? Or have they, for some reason or other, not spread out and done terraforming? We really don't know the answer to this. But we're scanning the skies now to find everything we can and discover what's out there. And pretty soon we'll have some answers. Now, knowing it's possible that other races could exist and could already be sending von Neumann probes all over our galaxy, and that they might be using nanotechnology to do terraforming or exploring, the question is, what would we do if we discovered nanotech dust headed for our planet? I know that sounds unlikely, but it's possible if you were a conscientious builder of terraforming hardware, that you would program such machines to destroy themselves automatically when they hit an oxygen atmosphere, and that would be one of the methods you'd use to prevent them from destroying someone else's planet. But we can't assume that everybody out there has the same sort of morality as we'd like them to have. After all, look how badly we've treated our world and our people. It's an awfully sobering thought to know that there could be unknown eyes watching us from the dark, and their machinery could already be on the way. I'm Sir Charles Schultz, and this has been Talk Universe.